Ladies and gentlemen, dear friends, participants in the BIMC 2023, we all know that every effort should be rewarded. All of you showed exceptional skills and knowledge in the field of mathematics. Congratulations on the high results and successful performance. Congratulations to the participants from
Bangladesh, Bolivia, Botswana, China, Cyprus, Ghana, Hong Kong, India, Indonesia, International Girls Team, Kazakhstan, Korea,
Kyrgyzstan, Macau, Mexico, Mongolia, Nepal, Peru, the Philippines, Republic of Uzbekistan, Romania, Russia, Singapore, South Africa,
Sri Lanka, Taiwan, Tajikistan, Thailand, United Arab Emirates, the United States of America, Vietnam, Bulgaria. Congratulations once again to all of you.
Dear participants, leaders and friends, we are in the final stage of the 2023 International Mathematics Competition. Bulgaria and Burgas had the honor to host this exceptional forum for young people for the third time. Smart and talented young people in whose faces the future can be seen. We are convinced that each one of you has represented your own country in the best possible way. We believe that behind each of us there is another person, almost invisible, who supports and guides us, who helps us make our own discoveries and make our dreams come true, without whom we would not be who we are today, having knowledge and skills, proud of what we have achieved.
So today, with deep respect, we turn to all the team leaders and deputy leaders who did their best to keep the spark and the fire in you and lead you to the depths of science. So let's say together, thank you.
This is the time to express our gratitude to a person whose energy and spirit every time makes this World Forum of Youth Enthusiasm and Love of Science possible. A person dedicated to young people and the future. Let's say it together. Thank you, Dr. Venxian Sun.
We give special thanks to the jury, the entire technical team, and everyone who made this competition possible.
And finally, let's express our gratitude for the support and dedication to our hosts, the municipality of Burgas.
We also personally thank the great friend of the young people, the mayor of the city, Mr. Dimitar Nikolov, who turned Burgas into a place where science and education are praised in order to meet all the challenges of our time and find the right path to the future. We thank you once again.
You know what? I have to admit something.
What's wrong? Tell me.
In this celebration and festivity, I'm a little sad. Do you know why?
Sad? Why are you sad? What do you mean sad? Today is the day of medals, of trophies, of celebration. Today everyone gets the recognition they deserve.
Okay, wait a minute. Everyone knows that, but think about where you are right now and what you see in front of you. I know young people live, learn, share, and have fun on the internet, but on a day like today, I would like all of that excitement, all of that expectation to be shared live. Now, just for a moment, imagine our summer theater full of thousands of smiles. Imagine the emotions and the joy.
Now, it will happen someday, but let us not be sad. Let's try, even though online, to get together and being together for a little bit. So, let me remind you, it's not only by chance that we started our journey with a Bulgarian folk song which was included in the Voyager Golden Plate aboard the Voyager 2 and Voyager 1 spacecraft as a musical message from the Earth to the distant space, and to this day tells us about people. It has become a symbol of the strength and the spirit and the eternal quest of knowledge. Don't you know that wherever we are in the world, we share the same sky and stars? And you know, every country, every city has its own symbol, which are the living memory of every nation.
We, the citizens of Burgas, have a symbol that is an open door to the world, a symbol of freedom, hospitality, and friendship. This is the pier, and although it does not connect to shores, it connects the people with the sea and the world. During these 7 days, it was illuminated with the colors of the flags of all participating countries. But see for yourself.
Hello everyone, we are just a few hours away from the closing and awarding ceremony of the International Mathematics Competition Burgas, Bulgaria 2023.
We're more than happy to give the word to the most active members of the organization of the BIMC Burgas 2023.
Уважаеми доктор Сун, уважаеми състезатели, благодаря на всички участници за техните изключителни постижения на международното състезание по математика, чието домакин, макар и виртуално, за трети път беше нашия град Бургас. Искам от сърце да благодаря на целия екип, който виждате пред вас, и на тези, които не са тук в момента. Да благодаря на доктор Сун специално за подкрепата за организацията и за лидерството, на дяди Тунсом от Индонезия, който наистина беше част от нашия екип и подпомогна организацията на цялото състезание и всичко, което се случваше по време на състезанието. През всичките тези дни всички бяхте заедно, като представихте както себе си, така и своята държава и показахте своите умения, своите знания, свързани с математиката. Цялото наше състезание беше един своеобразен мост между поколенията, мост между държавите, мост между всички хора, които се опитват в века, когато настъпва изкуственият интелект, да приемат предизвикателствата, да не само да решават задачи, но и да създават такива, защото това е част от целия процес, който е изключителен и всичко това е математика. Аз се радвам, че отново Бургас беше мястото на провеждането на тази среща и желая на всички участници много успехи в всички аспекти на техния живот.
Аз ще добавя една огромна благодарност от името на целия колектив и учениците на Природо-математическа гимназия Никола Обрешков Бургас, към община Бургас, към доктор Сун, към целия екип на провеждане на това състезание. За нас е огромна чест, че Бургас отново е виртуален домакин. Надяваме се нашите деца да ни зарадват много след няколко часа на церемонията по награждаване и очакваме следващи предизвикателства.
Thank you to all of our guests who dared to share their time and efforts organizing the BIMC 2023. Now, we would like to give the floor to Mrs. Kitty Phillips from South Africa.
Greetings from South Africa. It is with great pleasure that I address you today at the closing ceremony of the Bulgarian International Mathematics Competition, hosted online by the Burgas municipality. This event has been an incredible journey filled with mathematical brilliance, cultural exchange, and the spirit of friendly competition. On behalf of all the participants and contestants in BIMC 23, I extend our deepest gratitude to the Mayor of Burgas, Mr. Dimitar Nikolov, whose unwavering support and vision made this competition a reality. Your dedication to fostering intellectual growth and international cooperation is truly commendable. I would also like to extend our heartfelt thanks to the Deputy Mayor of Burgas, Mrs. Yordanka Ananyeva, education expert Zhenya Georgieva, and all the members of the Planning Committee, as well as the staff of the High School for Mathematics and Natural Sciences in Burgas. Your meticulous planning, attention to detail, and tireless efforts behind the scenes ensured the seamless execution of this event. Your commitment to excellence is truly inspiring. A special mention goes to Mr. Tiadi Tongsun from Indonesia, whose invaluable contributions in developing the online platform, managing registrations, and capturing contestants' answers made this competition accessible to participants from all around the world. Your expertise and dedication have been instrumental in the success of the online events since 2020. To the esteemed members of the Academic Committee, I extend our sincere appreciation for crafting a set of high-standard questions that challenged the intellect and problem-solving skills of our young mathematicians. Your commitment to academic excellence is greatly appreciated. Clearly, we have education experts from around the globe. Throughout this competition, we have witnessed remarkable achievements, celebrated the diversity of cultures, and strengthened bonds of friendship. The opening ceremony showcased the beauty of Burgas, capturing its vibrant spirit and welcoming participants from around the world. It was a testament to the power of unity and the universality of mathematics. The Cultural Exchange Program was a true celebration of our global community. Through mesmerizing dances and captivating presentations, we had the opportunity to experience the richness and diversity of each participating country. These cultural exchanges remind us of the importance of embracing our differences and fostering a sense of global citizenship. The International Maths Seminar provided an invaluable platform for educators to share their knowledge, exchange ideas, and learn from each other's experiences. It is through such collaborative efforts that we can continue to elevate the standard of mathematics education worldwide. The puzzle challenge ignited the participants' problem-solving skills and critical thinking abilities. It was a thrilling experience to witness the contestants' determination and creativity as they tackled the hexamino puzzle. Congratulations to all the participants for their outstanding performances. Of course, the highlight of the competition was the individual and team mathematics competitions. The level of talent and dedication displayed by our young mathematicians was truly exceptional. It is through the international mathematics competitions that we can nurture and recognize the brightest mathematical minds of our generation. Today, we celebrate the achievements of the winners. However, each and every participant deserves our applause for their hard work, perseverance, and dedication. Your commitment to the pursuit of knowledge is truly inspiring. Participating in the Bulgarian International Mathematics Competition is not just about winning prizes. It is an opportunity to challenge oneself, to broaden one's horizons, and to learn from the brightest minds across the globe. The experiences gained through this competition will shape the future of these young mathematicians, opening doors to endless possibilities. Finally, I would like to pay tribute to the father of IMC and chairman of the executive board, Mr. Wen-Hsien Shun. Your vision and passion for mathematics education have brought together students from 31 countries, fostering a global community of young mathematicians. Your contributions have made a lasting impact on the future of mathematics. Your hard work, dedication, and unwavering support have brought us together year after year in the pursuit of knowledge and excellence. Your unwavering persistence in fostering a spirit of collaboration, friendship, and mathematical brilliance paves the way for a brighter future. Hard work. Looking forward, we hope that the next international mathematics competition will bring us together physically once again, perhaps in the beautiful country of South Korea. The prospect of meeting face to face, engaging in intellectual discourse, and forging lifelong friendships is something we eagerly anticipate. Thank you, and congratulations to all the participants and winners of the Bulgarian International Mathematics Competition 2023.
Thank you, Mrs. Kitty Phillips. We are deeply honored to give the floor to the members of the jury of Bulgaria International Mathematics Competition 2023 to comment on the results of the competition.
Dear participants, ladies and gentlemen, Greeting from Taiwan. Our academic committee is very strong and efficient. We produce high-level contest paper for BIMC 2023. We chosen suitable topics from the proposed programs submitted by each country, then revising it, and at the same time we add many different ideas and given a fair marking scheme. Our committee include international members. There is Dr. Simon Chua from Philippines, and me from Taiwan, Belaslav from Bulgaria, Jenny Lee from Taiwan, and Rena Eric Chua from Philippines. And also we have Professor Iluran from Romania. Also, we have Professor Rowe from China, and Mr. Teddy Thompson from Indonesia. We also have Mengxuan Wu from USA, and also Dr. Masta from Indonesia. We also have Brian Chen from USA, and Xinbo Wang from USA, and Yuchen Chu from Switzerland. And the local member include Konstantin from Bulgaria, and Professor Emil from Bulgaria, and also Mr. Dingo from Bulgaria. Also, we have Galadin from Bulgaria. First of all, I want to explain how to select the BIMC 2023 contest program. We first correcting the proposed program from participant countries. Exclude the past question. There are some questions copied from past competition. Due to the ranking and the chosen the program from the proposal program, we try to select at least one question from the country that submit the proposed programs. According to the ranking scores, the 4 types of questions with the highest score are selected from algebra, number theory, geometry, and combinatory. Each jury is responsible for revising the description and the solution of 4 questions, given alternative solution, if any. At the same time, some questions are given a marking scheme. Thus, the problem need detailed solution. Make the first draft, then each jury review it and also given a suggestion, alternative solution, revising to each problem. Make the second draft by eliminate some problem and review for the text of the problems. And prepare the first version of the contest paper based on the revised question. Then, according to every jury's comment, make the second version of the contest paper for double checking. Then, we determine the final version of the contest paper based on the revised by the juries. Those processes take about 2 months in total. We provide consultation for non-official language country that require translation. Each jury then marks the assigned question and double-check the question the other jury have marked. Double-check the student's answer, which are different scores, and the moderation with the team leader and given the final score. After the score of the contestant are determined, a team leader meeting will hold to determine the award score.
This is analysis on key stage 2, team question number 2. So this is the condition of the problem. Alex buys a lunch, and when receiving his change, he receives dollars instead of cents and cents instead of dollars. And after buying a slice of bread for 15 cents, he realizes that the amount of money he has at that moment is twice as big compared to the amount of money he should have if everything was correct. And the question is, how many dollars and how many cents is the correct change? So the solution of the problem actually consists of 3 main steps. The first one is to obtain expressions for the amount with correct change and without the correct change. The second step is to derive an equation from the information given in the condition of the problem. And the third step is to solve the corresponding equation and to find the final result. So the first step, if we take that the correct change is $6 and Y cents, then the amount Alex should have is 100x plus Y minus 15, which according to the marking scheme is 5 points. And if we change the places of X and Y, we obtain the amount he actually has at that moment. So what are the main difficulties here? First of all, if the student chooses another unknowns, for example, the amount that is paid, then he gets another equation, which is a bit more difficult. And the common mistake is that the students, they do not know how to derive information from the condition of the problem, and sometimes they forget to subtract 15 cents. The second step is to derive an equation from the condition of the problem, and this is the condition of the problem, and this equation becomes the following one. So what are the mistakes here? So some students make mistakes when making these simple algebraic manipulations to arrive to the final equation. And the third step, of course, is to solve this equation. There are many different ways to do so. One of them is just to plug in the values of x. Since x is less than 20, you just plug 1 to 20 and see what happens. And if we notice that x is odd, then we may do this with only odd numbers. And the more elegant solution is if we write the equation in this form, y equals 2x plus 3 times x minus 5 divided by 98, and to conclude that x equals 5. And what are here the main problems for the students? some of them solve this equation just by trial and error, and when they find one solution, they make the assumption that this is the only one solution, and they don't actually understand that they have to find all the solutions. And what are the overall conclusions from this problem? So in some sense, the problem is straightforward, but for the more experienced students, and in general, it turned out that this is a difficult problem, and it was solved completely only by 6 teams out of 70.
Assalamualaikum warahmatullahi wabarakatuh. Hello everyone, my name is Al-Azhari Masta. I am one of juris member BIMC 2023. First of all, I would like congratulations to all participants, teachers, and team leaders for your success in BIMC 2023. In this section, I will give some comment and summary for team contest problem number 4 in case 2. There are 8 circles on the rectangular board as shown in the diagram below. The distances between any pairs of adjacent circles, horizontally or vertically, are all equal. Boris wants to color some circles in red. How many ways can Boris color some of the circles so that the resulting board has no line of symmetry? There may be many ways to solve this problem, but in this section, I will explain the juris solution. For convenience, we also consider the board without any coloring. If we consider the coloring of circles, there are 256 possible configurations of the board, including the board without any coloring. If we calculate how to color the circle that obtain horizontal line symmetry, there are 16 configurations for the resulting board that have a horizontal line of symmetry as shown in the following condition. And also there are 16 configurations for the resulting board that have a vertical line of symmetry as shown in the following condition. If we consider the horizontal line symmetry and vertical line symmetry, there are 4 configurations for resulting board that have both horizontal and vertical line of symmetry as shown in the following. So the total number of ways to color several circles so that the resulting board is not line symmetry is the total possible board configuration minus the total configuration for the resulting board to be vertical or horizontal symmetry. So we can obtain there are 228 ways to color at least one circle so that the resulting board is not symmetrical. The marking scheme for this problem, if a student count the number of possible coloring board include without coloring, they will obtain 5 marks. Also, the number possible coloring board has horizontal line symmetry, they will get 10 marks. Observe the number possible coloring board has no vertical line symmetry, they will get 10 marks. Count the number possible coloring board has both vertical and horizontal line symmetry, they will get 5 marks. And if they find the correct answer, they will get 10 marks. So if the student get the perfect answer, they will obtain the 40 point. Almost students can solve this problem. Most students answered by counting one by one how to color the board so that the resulting board has no line symmetry, starting from the without any coloring, one coloring circle, and two coloring all circle. But by using this way, some of them make a lot of mistakes in calculation. This problem is good for practicing logic, critical thinking, and practicing imagination to solve this problem. Maybe that's my summary and comment for this problem. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.
Hello everyone, my name is Yuchen Chu, and I would like to talk about the team question number 6 of Key Stage 2. Let us first take a look at the question. It says that the number 3 has the following properties. It is 1 less than a square number, and 5 times of it is also 1 less than a square number. The question then gives another example, which is 24, and asks what is the smallest number with the same properties that is greater than 25. We have provided 3 sets of solutions for this problem. I want to first briefly mention that to solve this problem, a certain amount of trial and error will probably be involved. Therefore, if the student can do some mathematical analysis to the problem first, there will be fewer cases to be examined, which might save a lot of time and also decreases the chances of making a mistake. So now let us take a look at the solution 1. The key idea here is to do analysis on the possible remainder of a square number under modulo 3 and modulo 7. And based on these observations, one would only have to check that n equals to 8 does not lead to the desired answer. But the next case, when n equals to 13, it works. And the marking scheme is here for your reference. For solution 2, if one simply tries all the possible cases, you will find that from n equals to 6 to n equals to 12, it doesn't work. And then you will also get that when n equals to 13, it gives our desired answer. So here is the marking scheme. So for solution 3, one might consider the possible remainder under modulo 5. Based on the unit digit, one would only have to check the cases for m equals to 14, 16, 19, and 21, 24, 26. And these are the cases that doesn't work. And one would also show that 29 gives the desired answer. So the marking scheme is also provided here for your reference. And here are some of the observations that we have made. So first of all, 9 out of 82 teams get the full marks, but also 8 teams got 35 marks, where 5 marks are more or less deducted for missing some cases, or some teams solve the question but write down the wrong answer. Also, there are a lot of students simply list all the cases and put a cross to the cases that doesn't work without any further explanation. We take away 5 marks since writing down the solution clearly and correctly is also important for learning mathematics. For example, there are many teams that do the calculation correctly for every cases, but they just simply leave all the cases, and then they fail to recognize that A41 is a square number, so they miss the answer. Also, a statistic might be of your interest is that out of the students who solve the problem or on the right approaches to the problem, the ratio of teams following solution 2 by trial and error basically And also solution 3, by consider the remainder under modulo 5, the ratio of these two types of solution is around 2 to 1. And there are only 2 teams from Kazakhstan that have considered the remainder under modulo 3. But no teams has considered the modulo 7. And also some teams try to observe the patterns, some patterns for the properties, and this would be interesting if one would be able to prove such pattern is indeed the case, is true. Anyway, for a summary, I think a takeaway for students from this question is the importance of writing down your thoughts and solution carefully. It will not only help others to understand you, but will also keep yourself from making mistakes. Okay, thank you.
Hello everyone, my name is Mr. Galin Totev and I was part of the jury committee of BIMC 2023. Today I will present analysis of key stage 2 team problem 8, which was quite hard geometry problem. Okay, firstly let me introduce you to the problem statement. You are given triangle ABC and its angles. You know that angle BAC is 120 degrees and angle ABC is 40 degrees. After that, a point N is chosen on the line segment AC in such a way that AN is equal to AB. Then, point M is selected on array BA in such a way that AN M is equal to 40 degrees and M is after A. We are asked to find the angle measure of angle BMC. Now, this was quite hard problem and it cannot be solved with properties of triangles alone. We must make a construction that will allow us to make full use of the properties of the given configuration. One possible such construction is to construct the angle bisector of angle BAC and select a point key on BC such that BAK is equal to KN is equal to 60 degrees. Now, we can try to look for congruence triangles in this configuration. We can see that ABK and ANM have the same angle measures. And since from the problem statement AB is equal to AN, this means that they are congruent by ASA. Now, we can also observe that BAK and KN are also congruent because they share a key. AB is equal to AN and the angle between these two is 60 degrees. And from there, we can deduct that BK is equal to KN is equal to NM. Now, when we have found that, we can observe triangles KNC and CNM. We know that KN is equal to NM, and we can try to compute the angle measure of KNC. So, we can observe that because ANK is 40 degrees, KNC is 140 degrees, which is also the same as M and C. From there, these two triangles are also congruent by ASA. And because they are congruent, and we can observe that NKC is isoscale triangle because angle NKC is 20 degrees, this means that KN is equal to NC equal to NM. And from there, we can easily observe that angle NMC is 20 degrees, which leads us to BMC being 100 degrees. Now, the marking scheme that has provided for this solution is the following. For making a construction that can lead to solution, in this case, the introduction of point key, we give 10 marks. Then for observing the first congruences, we also give 10 marks. And for observing the consequences of the congruences, which are that CMN and CKN are 20 degrees, we then again give 10 marks. After that, for the final calculations, we also add the final 10 marks. Now, I can present another idea of how to introduce point key, which is the same key but introduced in another way. We may observe that AB is equal to AN, which means that ABN is isoscale triangle. This can lead us to the idea of constructing AK as a perpendicular bisector, and from there we can conclude the similar properties of the problem. Okay, now I would like to say a few words about some students' ideas that were presented here. One thing that some teams did, and it was actually shorter than our solution, is to observe directly that triangles AKC and AMC are congruent, and from there get angle BMC equal to AKC equal to 100 degrees. Also, some students decided to use trigonometry, which was quite useful in this configuration, but this is a little too advanced for IMC, so not all of the participants were able to do it in this way. Okay, and as a final info, I would like to say that only 14 out of 82 teams managed to solve it, and the trigonometry they used was the sine form of Trigucheva theorem. Okay, I hope you enjoyed this problem and hope to see you next year on Key IMC 2024. Bye!
Hello, my name is Konstantin Garov, and I will discuss the last question on the team contest for K-Stage 2 from the BMC 2023. So, in the statement, a rhombus shape is given, formed by 25 dots, in which the distance between any 2 points are equal, any 2 adjacent points, and the question is what's the number of the equilateral triangles which can be drawn with using 3 from these 25 dots as vertices. So, in the solution we first have to notice that there are 8 types of triangles, equilateral triangles, contained in the grid, yes. And then we need to count how many instances of each one of the triangles there is in the grid. The simplest possible triangle is the single triangle, and we can easily count that there are exactly 32 of these. The next simplest one is the triangle formed by 4 smaller triangles, and again, similar to the first case, we count that there are 18, 3 per every line. That's 3 times 3, and then 2 times for the other orientation. We go one size bigger with triangles with side 3, and here we have 2, 4 for each orientation, times 2, 8 in total. The biggest possible triangle of this type is the triangle of side 4, and we can clearly see there are exactly 2 of these. The next one, we move to triangles which have their sides not along the sides of the rhombus. And this is a bit harder to count, but as we can see from the pictures, there are exactly 18 of these in the grid. Next one is a little bit tilted. Then we can see that there's exactly 2 of these. Actually, it was a little bit mistaken. So the case G is the picture here, and there are 2 of the triangles of type G. And the case F is drawn here, and there are 16 triangles of this type. So we have 4, which are drawn here below, and then we have 4 possible symmetries. That's why we have 16 in total. And case H, we have 4 symmetries, and for each orientation there is exactly 1 way of fitting the triangle in the grid. And we sum everything up and we get 100. This is a marking scheme. For each case we awarded 5 marks. 2 marks are awarded for just mentioning the case, seeing the triangle is contained, and 3 marks for correctly counting the number of instances. So generally, as we can probably see, there were a lot of partial points given on this question. A lot of people saw only the first 4 cases, which were the more natural triangles, and most people counted them correctly. So, and for this, as we can see, 4 cases, they were awarded 20 points. Some people only found the first case, which and counted it correctly, which is by on marking scheme 5 points. But then even people who saw, so then we have the triangles type, the 5th type and the 7th type. Generally, when people saw the triangle from 5th type, they also saw the triangle from 7th type. And they counted them correctly. I think the other bottleneck was people forgetting for the 4 symmetries in the 2nd case and 4th case, or making some other mistakes. So there were a lot of people who had at least 30 points, but I think we had only a few teams who got the answer right by the end. But generally, I think it was the problem was well done, given the fact that it's the last question and supposedly the hardest from the 2 contest. But thank you.
Hello, my name is Li Zhening. I will give a brief analysis on our number question of team contest, Key Stage 2. Since only numerical answers are required for the question 1, 3, 5, 7, and 9, we take a look for the number of teams finding the correct answer. From the table, question 7 is the one that the fewest number of teams answer correctly. So in the following discussion, I will introduce some ideas to solve this question. This is the question. And you can find all solutions by trying all possible values for A, B, and C. But you must be very patient since the answer is unique, which is H equal to 7 and B equal to C equal to 17. And now we can divide the rectangular bar into 2 parts according to whether it can be seen from vertex A or not. The visible part is weight unit Q and the invisible part is weight unit Q. It is more clearly when we view from the outside vertex of vertex A. We have 2 ways to express the number of visible unit Q. The first way is count directly. And another way is all unit Q minus the invisible unit Q. And from B, we can conclude that A, B, and C have the same parity since 487 is an odd number. This is an important property since this can reduce the number of possible cases. This solution 1 is using the first formula. But in this solution, we use a T for factorization. HC times C minus 1 to both sides, and then we can factor the left-hand side. And here we find a solution when C equal to 17. But we still need to search since the question is asking find all solutions. And here, when we try to C smaller than 13, we have right-hand side greater than 2C minus 1 square. Thus, there is no solution, and then we can stop the search. And then we have the unique solution and find the number of unique Q that are not visible is 1536. And another method is using the second formula. And we would need to find the value range for C. And using the formula, if C is smaller than 14, the number of the visible cube would be smaller than 469. This one is impossible since the question is tell us the number is 487. Now we must have C is between 14 and 20. And we also need another property. The values of A and B move in opposite direction when C is fixed. And this is the proof. And for each C, we can solve for the value range for A and then solve for B. And we also, here we can conclude the expression for B. And here, don't forget we have an important property. A, B, and C all have the same parity. So when C equal to 14, A and B are both even numbers. So here we just need to discuss A equal to 10. And in this case, no solution. When C equal to 15, A and B are both R numbers, but this also no solution. 16, no solution. And this is 17. And we find a solution when C equal to 17, but we still need to search since the question is finding all solutions. So 18, no solution. 19, no solution. 20, no solution. So we find the answer is unique. And the method is using the same idea of solution tool, but using the first formula. And we also can conclude that C is between 14 and the 20. Then for each C, we solve for the possible value for B, then solve for A. At least here, when C equal to 14, we can equation A into the form. And since A is a positive integer, so 669 over B plus 13 is greater than 13. Then we factorize 669. And we can find the B plus 13 equal to 1 or 3. But both cases are impossible since B is also a positive integer. Using the same idea, we can check when C equal to 15, no solution. 16, no solution. 17, we have one solution. 18, no solution. 19, no solution. And 20, no solution. So we can get the unique solution, and the answer also is 1536. So that's all my comment to the question. Thank you.
Hello, this is Wei Luo. I'm going to talk about problem KS3 individual B1. The problem is what's the number of real number solutions of the equation x squared minus 8 times integer part of x plus 7 equals 0, where we have this notation denotes the largest integer which is not greater than x. For example, this gives 3, this gives minus 4. Be aware that integer part of minus x may not equal to minus integer part of x. The main idea of this solution will be deriving a range for the variable x and check case by case. We have 3 equivalent ways of deriving the range of x. The first is in terms of the integer part of x. We will use integer part will be less than this one, and that's the integer part plus 1. But you need first to find that use something to prove that x at least should be greater than 0 from the equation. Then you can find the equation for integer part, which is this will be smaller than 0. But without this condition, the derive this inequality directly will be it's a wrong inequality. But we can have an easier way to do that, derive inequality in terms of x, which is x squared minus 8. Since x integer part should be no greater than x, so this large at least. Now we can have x belongs to the interval 1 to 7. And we have some equivalent way of deriving that in terms of the fractional part. And this one will be x minus integer part and belongs to 0 to 1. You can need to write 8 squared minus, let's say, 8x plus 7. We have plus 8. This will be 0. And we can have 8x plus 8x minus x squared minus 8x plus 7 will belongs to the interval 0 to 8. Then you have two inequalities. After having the inequality, you know the range. You can check case by case. You have 4 solutions corresponding to the integer part to 1, 5, 6, 7. And the marking scheme for this problem is we basically have 10 marks for deriving the correct inequality and 10 marks for finding the correct solution, 4 solutions. But if you only give the answer 4, you have no marks. Things we can learn from this problem is that whenever you have integer, some equation involves integer part, you will always use an inequality like this. Another thing is when you want to solve a Diophantine equation, you always need some inequality to bound the variables. And for the performance on this problem, the points, 20 points and 2 points appears very often. This 20 points, of course, is for a full solution. But this 2 points is for, you only find 2 solutions, 1 and 7, which corresponding to x with an integer. But you don't know how to deal with the integer part function, and you cannot find that there are 2 other solutions, some square root of a number. So that will give you only 2 points.
Hello, this is the analysis on Key Stage 3 individual question, Section B, number 2. My name is Simple Wang. The question goes as follows. Consider a regular hexagon. Paul wishes to color each of the vertices in green, red, or blue, in such a way that there are no neighboring vertices colored the same. What is the total number of ways Paul can color? Here is an example of proper coloring. As you can see, for this vertex, the left end is colored red. The right end is colored green. So there is no rule violated. And similarly for this edge, the left end and the right end are colored differently. To solve this question, one way is to enumerate all possible colorings. For example, you may start with RGR, which stands for red, green, red, and so on and so forth. Enumerate all possibilities, and then you move on to RGB and enumerate all possibilities, and then RBR, and then RGB, and so on and so forth. This way, you're guaranteed to enumerate all possibilities, and you will get the final answer 66. When grading this question, we actually follow a very strict marking scheme. That is, if we only see 66, we are not going to give any point. We're only giving point if we see the student's work. There's one thing I want to remind teachers and students, that when you are using brute force, it is very important to keep things simple. Use a strategy that is easy to execute and easy to double check. This way, when you obtain an answer, the answer is more likely to be correct. There is another way to solve this question, namely, forget about the hexagon and think about there are vertices lying in a row. Without loss of generality, let vertex 1 be red. And then we will let Rn, Gn, Bn, where n can be 1, 2, 3, 4, and 5, or any integers, be the numbers of colorings where the last vertex is red, green, or blue. With this notation, we can now study the recurrence relation among Rn, Gn, Bn, Rn plus 1, Gn plus 1, and Bn plus 1. Once you obtain the recursive relation, you can solve for the number of colorings. When marking this question, we will give 10 points if we see the student attempt to establish a recursive relation, and then another 10 points if the final answer is correct. There are about 100 students get the full credit. 80 of them answer 66, and about 20 of them answer 14, where 14 is the number of colorings if the hexagon is unlabeled. That is, if one coloring after rotation matches another coloring, then they are considered the same coloring. If the student interpreted the question in this way, we will also get full credit. Beyond those students, there are 40 students that made mistakes. However, if the structure of the student's answer is clear, and it is clear that where he made the mistake, we will also give partial credit to award the part of the works that are correct. Thank you very much.
Hello, good morning. I'm Teddy Thompson. Will give you analysis on Key Stage 3 individual question part B, question number 3. The problem is in a triangle ABC, M is a midpoint of BC, and we draw the circle with center O that passes through the point A and C and is tangent to the line EM. The extension of BA intersects the circle at D, and the extension of CD intersects the extension of MA at P, as shown in the diagram. Prove that OP is perpendicular to BC. In the proposed solution, the first step is we try to let N the midpoint of CD, so Cn equal to Dn. And then since M is the midpoint of BC, so we can conduct that MN is parallel to BD, and hence we got angle BDC equal to angle MNC. And after that, since EM tangent to circle O with an alternate angle on triangle ADC to line EM, we will get the angle MAC equal to angle BDC and equal to angle MNC, and angle DAP also equal to angle DCA, like shown in the animation. And then hence EM, C and N are concentric, then we can conclude that angle A and M equal to angle ACM and angle DAN. And next, we try to draw line AO, AN, NO, DO, and CO. Since DO and CO are the radius of circle O, and CN equal to DN, so we can conclude that angle DNO equal to angle CNO and angle PNO, which is 90 degree. And then the radius AO is perpendicular to EM, so angle PAO equal also to 90 degree. Observe that triangle PAO and PNO have the same line OP, and then angle PAO, angle PNO, which is 90 degree, face to the line PO, and that makes A and O and P are the concyclic. And then since A and O and P are concyclic, we can compute the angle chasing like this one, and we can conclude that angle PON equal to angle PCR. And this make triangles PON and PCR are similar, and then the final conclusion, angle PNO equal to angle PCR, which is 90 degree, and this show us that OP is perpendicular to BC. For this proposed solution, the marking scheme like this one, the main idea to add N, the midpoint, and also found this angle equal, so we will give in 5 marks. To show that AMC and N are concyclic, 3 marks. To show angle PAO, PNO equal to 90 degree and prove that A and OP are concyclic, we give 8 marks. And then the final, to show angle PON, angle PCR equal and complete the proof, we give it 4 marks. Okay. For this solving this question, the proposed solution, we the basic main concept that we use is the first is angle case, and then the students should understand also the property of circle and also cyclic quadrilateral, and understand enough about the similarity. The contestant performance in this question, 12 contestants got a full mark, and then 25 contestants get a partial mark, and 279 contestants get not solve the problem and get 0 mark. It means the problem is very hard and very strong. The future suggestion in answering geometry problem is write the explanation for each step clearly and not only put some equation or drawing. Solving geometry problem need 2D and 3D inside, so solving geometry puzzle will help you. Observe another way from the official solution. That will help you. And I will show you one of the answer from the contestant is very good, who got the full mark, which is from China. In this solving this problem, he used alternate solution, is very good, and then he write the solution is very clear, step by step like this one, so everybody can understand. Then, and I hope all of you can do the same approach in another question. Okay, that's all from me. Thank you.
Hi everyone. I wanted to share with you a few comments on Key Stage 3 team contest, problem number 2. That was a very easy geometry problem, and the fact that it was very easy was proven by the fact that we have 51 perfect solutions with 40 points. So we have 51 out of 80 teams who actually solved the problem. And the other thing is that almost everyone who attempted to solve the problem, they got at least 10, 20 points, because according to our grading criteria was very relaxed. So we were actually giving, 10, 20 points for, showing some 90-degree angles, some isosceles triangles, etc. The proof itself consists of 2 major parts. The first one was that the students had to prove that AD is perpendicular to XY. So these were 2 lines. So ABCD is a rectangle, and one of the sides was perpendicular to a segment in a circle XY. So that was the first portion, and that was awarded with 20 points. And then the other 20 points were given for proving that the center of the triangle XYD lies on the segment AD. The first and the second portion, they could be proven by using several different methods. So we saw a number of different solutions, although most of the students, they calculated some angles, they used some isosceles triangles, they actually showed a very good knowledge of similar triangles. They used one of them even used actually analytical geometry. There were various approaches, and again, due to the fact that it's a relatively easy problem, you could actually approach it from different ways. Now, some common mistakes, what students did wrong. As I said, almost everyone who attempted the problem, they got some points. So the fact that we got 51 out of 80 perfect solutions means that it was actually a good, easy problem. Now, common mistakes, some students actually didn't even attempt to solve the problem, which was, I believe, a mistake, because as I said, if you just show a few angles, if you show a few isoleces or similar triangles, you were already getting some points. There were some students who actually misunderstood what had to be proven. This was one of the classical proof problems. Unlike other problems where you had to give a number, where you had to find something, here you just had to prove something. And of course, we had a few students who actually tried to cheat a little bit. They were just saying that some obvious things, but in fact, those things were things from the text already, or they had nothing to do with what had to be proven. So overall, I'm really happy with the performance of the students. It was a good, easy geometry problem, and I believe that all the students did a great job.
Okay, good day everyone. So for today, I will be discussing the analysis of Key Stage 3 Team Number 4. My name is Rener Chua. I am from the Philippines, and I was tasked to moderate this problem. So first, let's go to the question. So Dinko has placed some marbles into 100 black bags, which are numbered from 1 to 100. Each time, you are allowed to ask Dinko about the parity of the total number of all the marbles in any 15 bags, and Dinko will give you the correct answer. What is the least number of times you need to ask Dinko in order to determine the parity of the number of the marbles in bag 1 correctly? Show an example and prove your answer. Okay, so this problem, you will first need to look for the least number of solutions. Okay, and that is that is 3 times. So one way of doing it is such, and if you do it this way, you will notice that the parity of the numbers in bag 1 is equal to the sum of the parities obtained from these 3 questions, since number 1 appears thrice and all others appear twice. Okay, so since this is a correct solution, we just have to disprove. So we claim that 3 times is minimal, and we disprove that it is impossible. We prove that it is impossible to do it twice and once. Okay, so this 2. So here, so basically the marking scheme is just twofold. If you give one correct example, it's half of the points, and disproving it, the 2 and 1 scenario would be the other half. Okay, giving an answer of 3 without a correct example, example is 0 marks. Okay, this is what we use for this one. So our idea in marking, again, is we're just looking for the 2 main parts. Show and justify one correct example, and that asking 3 times works. That's the first half. And asking to answer twice is not possible is to complete the full proof of the problem. Okay, so out of the 80 Key Stage 3 teams, only one out of 80 got full marks, and 9 others got some partial marks. So maybe they got some examples correct, or some ideas correct. They got 9 marks. And we only got a total of 230 points total from all of the teams for this problem. So this is second to the last in terms of total number of points gotten from a question in the team contest. Second only to question number 7. Okay, so this became one of the most harder problems in the team competition. And the remaining teams got 0 marks. We noticed that it's either they really intentionally left it blank, so they don't have an idea of how to solve it, or most that tried to attempt answered 15 or 16. Okay, so that's the more trivial way of answering it, maybe. But most of the teams answered 15 or 16 as their answer. Okay. So our general comment, or my general comment for this problem is, this problem, usually in IMC, as part of the jury, we try to include these kinds of problems, or in the problem that you don't really require a lot of technical math knowledge, but just more on creativity and logical thinking. This way, it's a striking balance between very technical question versus something that is like this. It's more of a logical question. Okay, so students, I hope that from this you can after the contest always try to look at where your mistakes at, and of course from there you'll improve, right? So next time you encounter such kinds of problems with regards to something like this, parity and just logic, hopefully you'll be able to solve it once you encountered it in the future again. So I hope you guys enjoyed this problem, and we'll see you in the next IMC. Bye-bye.
Hello. I will be discussing Key Stage 3 Team Question 6. In this question, we're asked to consider an infinite arithmetic progression of positive integers such that no term of the progression appears in the Fibonacci sequence. And we're asked to find the minimal common difference for which this is possible. Solving this problem roughly requires one or two math arguments followed by some amount of brute force-ish casework. So we'll go over those things in turn. The first lemma is that the Fibonacci sequence is periodic mod n for any positive integer n. You can observe this fact just for all relevant n from 2 to 8 basically, because the answer is 8 and you need to check all the n before that just by listing terms of the Fibonacci sequence mod n. And this works because any term of the Fibonacci sequence mod n is determined by the two previous terms mod n, because the Fibonacci sequence uses this additive equation that can be reduced to mod n. And once you've listed enough terms to see two adjacent ones mod n repeat, then you know that the Fibonacci sequence cycles thereafter. Two side notes about this. One is that, in fact, any adjacent pair of Fibonacci numbers also determines the previous number mod n just by subtraction. And so this lets you know that the Fibonacci sequence mod n is actually like completely periodic. There's no possible like prefix that's not periodic before it enters the period. And that might allow you to eliminate some error conditions or mistakes when calculating these numbers. The second thing is that I personally like to define the Fibonacci numbers starting with 0. And most of the maths just still carry over. It's very minor, but you can read off some properties slightly more easily. Something you may want to keep in mind for future Fibonacci number questions. The way to do this without the brute force is simply to argue that if you look at pairs of adjacent numbers mod n, there's only n squared possibilities. And so by the pigeonhole principle, the sequence is infinite, there's more than n squared. Some pair repeats. Once you have a pair repeating, the Fibonacci sequence is also periodic from there. Cool. So the second lemma is a bit more subtle, and we wanted students to call this out. And this is saying is that for if we have a working arithmetic sequence a plus d and so on, the Fibonacci sequence has no term congruent to a mod d at all. Why is this not quite obvious? It's not quite obvious because the arithmetic sequence doesn't contain every term congruent to a mod d, right? It only contains terms that are greater than or equal to a. So if you take an example, the 4, 9, 14 sequence, this is 4 mod 5. Okay, so 34 is a Fibonacci number. It is 4 mod 5, and it is in this arithmetic sequence, but it's not in other arithmetic sequences that are 4 mod 5 if they start from 1,000,004 instead, for example. To argue this, we basically just want students to call out the fact that the Fibonacci sequence is increasing and unbounded, and the arithmetic sequence contains all numbers congruent to a mod d above a, and because that contains all numbers above a that are a mod d, and the Fibonacci sequence by lemma 1 has infinitely, if it has one, it has infinitely many numbers a mod d, and so then those must overlap. Cool. So those two lemmas reduce the problem to simply you need to check for each n whether the Fibonacci sequence covers all residues mod n. So for n equals 2, you need to check that the Fibonacci sequence has a 0 and a 1, and so on. So you do the checking for 2 through 8. You see that when n equals 8, the Fibonacci sequence contains no numbers 4 mod 8 or 6 mod 8. And so that's the answer. So if you use the abstract lemma 1 argument, you can reduce maybe something like half of the calculations, since you can stop once you find numbers that are cover all the different residues mod n for 2 through 8. And so that gives you a solution. And so for completeness, here is the full solution and the marking scheme. So in general, this was a somewhat difficult problem. And certainly a lot of students didn't have the clarity in explaining lemma 2 that we're looking to get. So just to keep in mind that the tricky logic there is something to watch out for. And there were also lots of different results in doing the actual arithmetic. So yeah, thanks.
Hello everybody, my name is Iulian Stolerio. I'm a professor of mathematics in the Faculty of Mathematics, University of Iași, Romania. In this very short video, I'll go through the analysis of problem number 8, Key Stage 3 Team Contest. This problem proved to be rather challenging for the majority of teams. Actually, more than 70% of teams scored 0 points at this problem. The problem is about placing 1600 points inside the unit square such that if you take any rectangular of area 1/200 and with sides parallel to those of the unit square, you'll find at least 1 point inside this rectangular. This problem asks if it is possible to construct such a configuration of points. If the answer is yes, then you should provide an example, but if the answer is no, you should prove that it is impossible. Well, the short answer is yes, it is possible, but you already know this is not enough to say so. You have to construct such a configuration of points, which is rather difficult, and then to prove that this configuration meets the requirements of the problem. We provided here 2 solutions for this problem. I challenge you to find the third solution or the fourth solution. I'll give you a hint at the end of this video. I'm not going through the solutions now. You can read them by yourselves. Just to say that both solutions rely on the placement of points that have different x or y coordinates, such that the final configuration of points prevents the construction of empty rectangles inside the square that have area of 1/200. In order to visualize these solutions, I have also added some figures at the end of each solution. Now, I would also like to comment on the students' performance on this problem. Many contestants have tried to construct a symmetrical configuration of points inside the unit square, but did not succeed. In my opinion, one needs more than 1600 symmetrically placed points inside the unit square to meet the requirements of the problem. Now, I'm not saying that the solutions that we provided here are the only ones or the best ones. You can also find by yourself other solutions. For example, you can start by placing points on the diagonals of the unit square and then place other points on some segments that are parallel to the diagonals. Some students tried this method during the contest, but they didn't go too far with the solution. I challenge you to try it at home. Well, another challenge would be to find the minimum number of points that can be placed inside the unit square such that the requirements of the problem are met. Is this 1600? Is this 1504 or even less? Just try it. I also added here some statistics associated to the problem. I found a correlation of 69% between the scores proposed by the team leaders and the final scores. This means that fair agreement in the scoring task. I also added in this presentation some bar charts for the student scores. As you can see from those pictures, the distribution of the scores for the problem is not normal. It is rather logarithmic. This means that most of the students struggled with this problem, which proved to be a rather difficult one. Only one team out of 80 teams solved this problem entirely and got 40 points. And only 25% of the teams obtained more than 5 points for this problem. So only 25% of the teams obtained non-zero points for the problem. Well, this is all for now. I wish you a very nice holiday if you are in holiday. and all the best for the future. I hope to see you in person next year in Korea. Bye bye for now. Bye bye.
Hi, my name is Mengshan Wu. I am a former lecturer at the University of Minnesota School of Statistics in the United States. Today, I'm going to present the analysis on Key Stage 3 Team Contest question number 10. In this question, we define a smart triangle of order n as an arrangement of the positive integers from 1 through n times n plus 1 over 2 in a triangular structure with n rows such that each number above the bottom row is equal to either the sum or the absolute difference of the two numbers immediately below it. And here we see some examples of smart triangles with orders 2, 3, and 4 respectively. Part A of the question asks for whether there exists an order 5 smart triangle with the numbers 1, 2, and 3 occupying the 3 corners of the triangle. And part B asks for whether there exists a smart triangle of order 6. Before we begin, here are some useful results. First, for an order 2 smart triangle with A and B in the bottom row, the parity of the number on the top row must be congruent to that of A plus B mod 2. Next, as a direct result, the sum of the 3 numbers in order 2 smart triangle must be an even number. Also, for any given smart triangle, its mirror images and rotations are still smart triangles. Let's solve part A of the problem. Observe that there are 7 even and 8 odd numbers from 1 through 15. Let us analyze the parity pattern of an order 5 smart triangle. For the bottom row, 2 and 3 already occupy the 2 endpoints, and we can fill even or odd numbers into the middle 3 cells in 2 to the 3 equal to 8 different ways. Among these 8 parity patterns of the bottom row, 3 of them yield exactly 7 even and 8 odd numbers for the whole triangle. Let us analyze whether each of the 3 patterns can produce a valid smart triangle by placing 4 through 15 into those blank cells. For pattern 1, note that the even numbers form 2 smart triangles of order 2, with the extra number goes into cell N. There are a total of 3 possible ways to group the even numbers from 2 through 14 into 2 smart triangles of order 2. However, when we consider the placement of the odd numbers, none of these three groupings will work. For pattern 2, the situation is similar to pattern 1. And again, none of the groupings yield a valid smart triangle. For pattern 3, we see that the 6 even numbers from 4 through 14 form an order 3 smart triangle. After some analysis, we see that there are 2 distinct order 3 smart triangles formed by the even numbers from 4 through 14, along with their reflections and rotations. Note that the number at cell H must simultaneously be either the sum or absolute difference of the numbers C and G, and the sum or absolute difference between the numbers K and M, where C, G, K, M are 4 distinct odd numbers from 5 through 15. These exclude the possibilities that H equals 10, 12, or 14. So we must have H equals 6. Among the 2 ways to put an order 3 smart triangle with numbers 4 through 14 into such a pattern, one of the arrangement yields a valid smart triangle when we consider the placement of the odd numbers, while the other placement doesn't work. This shows us there exists a unique smart triangle of order 5 with the numbers 1, 2, and 3 occupying the 3 vertices. Here, I would like to congratulate teams Mongolia 3B and United States 3A on finding this unique smart triangle satisfying the condition. Next, let us move on to part B. Again, we solve this part by analyzing the parity of the triangle. Here we denote the bottom row's 6 numbers as A through F, and then we express the parity of the upper rows in terms of A through F. After we are done, we add up these 21 numbers and found out that the result is even. This contradicts the fact that the sum of the integers from 1 through 21 is 231, an odd number. This shows that there exist no smart triangles of order 6. Another way of thinking is to group the 21 cells of a smart triangle of order 6 into 6 smart triangles of order 2, and the 3 vertices of the central smart triangle of order 3, namely G1, G2, G3. From a lemma we presented earlier, all the 6 red triangles have even totals. And with a little bit more analysis, we can also show that the vertices of the blue triangle G1, G2, G3 also add up to an even number. This again shows that If an order 6 smart triangle exists, then the sum must be even, which contradicts the fact that the sum of 1 through 21 is odd, and therefore there exist no smart triangles of order 6. A third approach is similar to the second approach, except that we keep track of the number of occurrence of even numbers in the smart triangle instead of the sum of all numbers in the triangle. Among the 80 teams, 8 of the teams have correctly proved or made a significant progress towards showing that an order 6 smart triangle doesn't exist. Note that these methods are not the only ones for proving the results. The China Team 3A and Hong Kong Team 3A each discovered a creative way of grouping, which shows that an order 6 smart triangle does not exist. Congratulations on all the teams that have solved this problem. Finally, here are some statistics of the performance of this problem for your reference. This concludes my presentation for today. Thank you, everyone, and goodbye.
Hello, my name is Din Kuranev, and I'm the member of the international jury at Bulgaria International Mathematical Competition 2023. I wish to congratulate all the participants, and I would like to share with you several details about the problems with numbers 1, 3, 5, 7, and 9 in K-Stage 3 in the team contest. Let's start with the problem number 1. This problem was solved by 28 from the participating teams, which is 35% of them. The next one is the problem number 3. It's a geometrical problem, and it was solved by 49 from the participating teams. It is 61.25% of them. And this is the highest result for these numbers. Again, geometrical problem. The problem number 5. It was solved by 43 from the participating teams. Again, more than half of the participating teams. And it is 53.75% of them. Maybe the hardest problem was the problem number 7 with so-called BMC numbers. What is the smallest BMC number for which we must have these conditions? You can see it on the screen. Very nice problem and very hard based on the results. The problem was submitted by Romania. Congratulations for them. This problem was solved only by 4 from the participating teams. It is 5% of them. These teams are Bulgaria C, Hong Kong A, Thailand D, and Singapore A. And the last one problem is the problem number 9. How many 7-digit positive integers with distinct digits are not divisible by 9? Also very good problem. At this problem we have 20 right solutions, which is 25% from the participating teams. As you can see, maybe the favorite problems was the geometrical ones for the participants, based on the results, of course. That was for me. Good luck to all of you.
We have some suggestion. In recent years, with the rapid development of the computer artificial intelligence, computing power can answer standard type of question faster and more accurately than human. Then, school mathematics education must take a big change to conform to this situation. For example, ChatGPT can answer a variety of questions. Therefore, developing students' creative is the focus of future education. IMC contest question must follow this trend. Human beings are different from computer or robot in that human thinking. They reason logical and make rational judgment, and they have ability to innovate. In fact, a computer only functions by human program, and writing programs requires deep mathematics. Therefore, we must cultivate children's interested in mathematics and the hobby of mathematical thinking as earlier as possible. I have repeatedly emphasized that mathematics is a self-taught, not a gift from others. Therefore, I am very upset students participate in conventional tutoring. Especially for mathematics elite like you, tutoring is not only restless but harmful. The content of mathematics competition from primary school to senior high school include 4 fields: algebra, number theory, geometry, and combinatory. You must study more knowledge in those fields. In the contest question of BIMC, although we have reduced the difficulty of the geometry question, but the average performance is not good, which shows that everyone's learning in geometry is not solid. Everyone should know that in the competition, it is impossible to win a good prize without scoring points from geometry problem. Taiwan Jiuzhang Mathematics Education Foundation provides a set of materials, self-study textbook for junior secondary school. Geometry have a chapter 1 to 8. This is Madame Kiki Phillips from South Africa assisted me in translation into English. You may free download and study from the website like this. And I am also very upset to only preparing for the mathematics competition by doing a lot of past contest questions. The topics of high-level competition like IMC are very innovative and creative, and the contestant must have a high-level skills. No matter you perform at IMC this time is good or bad, as long as you continue to work hard according.
Greetings from South Africa. It is with great pleasure that I address you today at the closing ceremony of the Bulgarian International Mathematics Competition, hosted online by the Burgas municipality. This event has been an incredible journey filled with mathematical brilliance, cultural exchange, and the spirit of friendly competition. On behalf of all the participants and contestants in BIMC 23, I extend our deepest gratitude to the Mayor of Burgas, Mr. Dimitar Nikolov, whose unwavering support and vision made this competition a reality. Your dedication to fostering intellectual growth and international cooperation is truly commendable. I would also like to extend our heartfelt thanks to the Deputy Mayor of Burgas, Mrs. Yordanka Ananyeva, education expert Zhenya Georgieva, and all the members of the Planning Committee, as well as the staff of the High School for Mathematics and Natural Sciences in Burgas. Your meticulous planning, attention to detail, and tireless efforts behind the scenes ensured the seamless execution of this event. Your commitment to excellence is truly inspiring. A special mention goes to Mr. Tiadi Tongsun from Indonesia, whose invaluable contributions in developing the online platform, managing registrations, and capturing contestants' answers made this competition accessible to participants from all around the world. Your expertise and dedication have been instrumental in the success of the online events since 2020. To the esteemed members of the Academic Committee, I extend our sincere appreciation for crafting a set of high-standard questions that challenged the intellect and problem-solving skills of our young mathematicians. Your commitment to academic excellence is greatly appreciated. Clearly, we have education experts from around the globe. Throughout this competition, we have witnessed remarkable achievements, celebrated the diversity of cultures, and strengthened bonds of friendship. The opening ceremony showcased the beauty of Burgas, capturing its vibrant spirit and welcoming participants from around the world. It was a testament to the power of unity and the universality of mathematics. The Cultural Exchange Program was a true celebration of our global community. Through mesmerizing dances and captivating presentations, we had the opportunity to experience the richness and diversity of each participating country. These cultural exchanges remind us of the importance of embracing our differences and fostering a sense of global citizenship. The International Maths Seminar provided an invaluable platform for educators to share their knowledge, exchange ideas, and learn from each other's experiences. It is through such collaborative efforts that we can continue to elevate the standard of mathematics education worldwide. The puzzle challenge ignited the participants' problem-solving skills and critical thinking abilities. It was a thrilling experience to witness the contestants' determination and creativity as they tackled the hexamino puzzle. Congratulations to all the participants for their outstanding performances. Of course, the highlight of the competition was the individual and team mathematics competitions. The level of talent and dedication displayed by our young mathematicians was truly exceptional. It is through the international mathematics competitions that we can nurture and recognize the brightest mathematical minds of our generation. Today, we celebrate the achievements of the winners. However, each and every participant deserves our applause for their hard work, perseverance, and dedication. Your commitment to the pursuit of knowledge is truly inspiring. Participating in the Bulgarian International Mathematics Competition is not just about winning prizes. It is an opportunity to challenge oneself, to broaden one's horizons, and to learn from the brightest minds across the globe. The experiences gained through this competition will shape the future of these young mathematicians, opening doors to endless possibilities. Finally, I would like to pay tribute to the father of IMC and chairman of the executive board, Mr. Wen-Hsien Shun. Your vision and passion for mathematics education have brought together students from 31 countries, fostering a global community of young mathematicians. Your contributions have made a lasting impact on the future of mathematics. Your hard work, dedication, and unwavering support have brought us together year after year in the pursuit of knowledge and excellence. Your unwavering persistence in fostering a spirit of collaboration, friendship, and mathematical brilliance paves the way for a brighter future. Hard work. Looking forward, we hope that the next International Mathematics Competition will bring us together physically, once again, perhaps in the beautiful country of South Korea. The prospect of meeting face to face, engaging in intellectual discourse, and forging lifelong friendships is something we eagerly anticipate. Thank you, and congratulations to all the participants and winners of the Bulgarian International Mathematics Competition 2023.
We have reached the long-awaited moment, namely the awarding of the participants.
Hello, my name is Martin Soldarov and I'm proud to represent Sofia Math School in this year's IMC. The problems in the individual and team contest were hard and I really enjoyed solving them. I want to thank Chairman Sun and his team for making this year's IMC. I also want to thank my teacher, Miss Elena Kisalova, for preparing me for the event. I'm really looking forward next year's IMC. Bye bye.
Congratulations to all the winners. You must be very impatient to find out which is the next country which will host the International Mathematics Competition in 2023. We would now like to give the floor to Mr. Park from South Korea.
Respected Dr. Son Mun-son, Chairman of the International Mathematics Competition Community, and Dr. Simon Sua, and Dr. Kidi, and Nijibate Karancho-Fai, and Dr. Ridwan Hassan Saparata, and Teddy, and the International Mathematics Competition all education family. Good morning, and good afternoon, and good evening, sir. I am Park Hyung-yang, Chairman of the Korea International Mathematics Competition Community and KET Educational Foundation. Thank you for your effort and the 2023 Bulgarian International Mathematics Competition Community. The 2023 BIMC, which was held non-face-to-face, because of the corona was successfully completed, and I am grateful for the community's efforts once again. Many participants will keep 2023 Bulgaria International Mathematics Competition as a memory for a long time. Their International Mathematics Competition education all family and their members. I want to call to the 2024 International Mathematics Competition in Korea. Korea already held International Mathematics Competition in Incheon, Daejeon in 2010 and 2014. In the first few years, because of the corona, International Mathematics Competition had to proceed non-face-to-face. I plan to hold the face-to-face International Mathematics Competition in Korea since the COVID-19 pandemic on July 29. However, it has not been finalized yet. The finalized plan will be notified to the International Mathematics Competition Community in November 2023. I'm waiting for you in Suwon, Gyeonggi-do, Korea. As the chairperson of the Korea International Mathematics Competition Community, I will work with other International Mathematics Competition Community to ensure a successful International Mathematics Competition. Korea is a very beautiful country and the people are very kind. I will be happy to see you guys in Korea next year. Their International Mathematics Competition all family. Please look forward to next year's International Mathematics Competition while watch the promotional video of Gyeonggi-do, which is holding the 2024 International Mathematics Competition. See you on July 29, 2024 in Korea. Thank you very much. Goodbye. International Mathematics Competition or Family. See you in Korea 2024. Welcome to Korea. Thank you.
We are at the Pier of Burgas, and here are the participants from the city in the BIMC 2023. Each of them already know the results and are now ready for the next competition. Because as they themselves say, if you love mathematics, it is for life. But now, let's not waste time. 31 countries participated in this year's competition, and it's time to hand over. In a few minutes, the lights of the bridge of Burgas will go out, and stars will fly in the sky, which will illuminate the long way to the future of this significant event. Thank you all for participating. We wish you many open horizons, success, ways forward and up. With this, we say no goodbye, and you're always welcome in our city. See you again, friends. Now, guys, let's count down. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. 0.